Hello friends, I am Lavanya Vaishnavi. Today we will start about Zener Diode. So what is a Zener Diode? What is the difference between the normal diode and the Zener Diode? So Zener Diode is a normal PN junction diode. So this is a PN junction diode again with high doping concentration. With high doping concentration. What is doping? Doping is nothing but adding impurities to your semiconductor device. So if I add more number of impurities to p-type and n-type semiconductor, then we call it as high doping or it is highly doped. Such highly doped regions are taken and formed a diode. Such diodes are Zener diodes. So where we will use the Zener diodes? Zener diodes are mainly used in voltage regulators. So it is maintained or it is mainly used in voltage regulators. What is this voltage regulators? You might be knowing the chargers of your mobile phones, right? So if you look at the charger of your mobile phone, you will be having an adapter. In that adapter, we can see that the output voltage is specified as 5 volts or normally it is 5 volts. So when I take this 5 volts, what does this 5 volts means? See, you have, where do we connect this adapter? We connect this adapter to mains, right? We connect that to mains. From this main, you will connect the adapter, then to the mobile device. Now, so this adapter, what it does it first converts your AC signal to DC. It converts AC signal to DC. In the previous classes, we learned how do you convert AC signal to DC and how does this DC signal, that is, it will be pulsating, right? So how does this pulsating DC is converted to normal DC signal, that is actual DC signal. So once it is converted to actual DC signal, because of the variations in the input AC, you may also find the variations in the DC output. That is, if it is 230 volts and you are getting 5 volts, it's okay. So suppose there is a variation in the power supply. If because of the variation, this 230 raised to 250 volts. Now what happened to the output voltage? Even this may also vary. Even this may also vary. Either it will increase or it will decrease according to the behavior of your input. Now, so if there is a fluctuating output, what happens to your electronic device? Your electronic device may get damaged. So what we will do? So we use a circuit which is called voltage regulator. These voltage regulator avoid such sort of fluctuations in the output. So such fluctuations in the outputs are avoided using voltage regulator. So this is one of the main application of Zener diode. Now coming to the symbol. How do you write the symbol of Zener diode? So this is the symbol of normal diode. Yes. So how do you write the symbol of Zener diode? This is the symbol of normal diode. To this normal diode, I'll just add two extra limbs like this representing a Zener diode. This part is anode and this part is cathode. This part is anode and this part is cathode. This limb is cathode. Now, to this, if I want to write the equivalent circuits, if you remember that diode, you had 3 models, right? So the one is ideal model, equivalent model and the piecewise linear model. Now, the same thing here you have 2 models, Zener diode equivalent circuits. So one is like this, like one is the anode terminal, because this is positive, negative, and this is cathode. This is forward by the resistance offered by the barrier. So I'll take it as VB. Suppose your Zener diode offers resistance to the flow of current, then the circuit will be like this. Anode, cathode, VB, and this is RZ. So the value of RZ is 0 here. The value of RZ is 0 in this. Like if it doesn't offer any resistance to the flow of current, then RZ will be considered as 0. If it offers, let us take the value of RZ. This is the equivalent circuit. Okay, so this is about the symbol. Next is characteristic. Next is characteristic of Zener diode. So the next one is characteristic of Zener diode. If I want to write the characteristic of Zener diode, I'll take normally voltage in x-axis and current in y-axis. So as I increase the voltage in positive direction, the current slowly start increase. So this is the behavior of normal diode. Here after VB, that is barrier potential, the current will increase. So what happens in the reverse bias? In the reverse bias, after certain voltage, this is Zener voltage. After the Zener voltage, the current increases abruptly. So you will be having a sudden increase in the current at the point Vz. So you operate the Zener diode in the reverse bias condition. We operate the Zener diode in the reverse bias condition at this Zener voltage point Vz. At this Zener voltage point Vz. This is about the characteristic of Zener diode. Now, Zener diode as a voltage regulator. So, voltage regulator is a circuit which accepts unregulated DC supply as input and gives a constant DC output without affecting the changes of the input. As I told you in the previous example, see here the input for voltage regulator is DC, right? So this is DC input and you will get a DC output. So if you are taking DC input and DC output, what is the use of regulator here? Here we say that the regulator monitors a constant voltage at the output. It will not attempt to vary the input variations in the output. It will not reflect the input variations to your output. If Vs is 5 volts, suppose I want V0 is equal to 10 volts and I have Vs is equal to 20 volts. So it gives constant 10 volts. Even if this 20 volts raises to 25 volts or if it decreases to 15 volts. Even this 20 volts raises to 15 volts or it decreases to 15 volts, the output voltage will always remains 10 volt. This is how a regulator works. So here Zener diode voltage regulator has a DC input and a DC output. DC input and DC output. And what is its property? It provides irrespective of your input, irrespective of the input voltage, the output remains constant. So this is what a regulator, voltage regulator is. Now the first one is Zener voltage regulator with no load. That is, I have not connected any load here. In spite of not connecting any load, how does this circuit works? The first thing is, so this is Vs is the supply voltage, Vz is the Zener diode. If you look at the Zener diode, this is negative terminal connected to positive and this is negative terminal which is connected to, this is positive terminal connected to negative, right? So this is the cathode terminal, we are connecting it to positive, anode terminal connecting it to negative. So this is how Zener diode is biased. That is, you have bias in reverse bias. Now let me apply KVL to this. Let us apply KVL to the given circuit. So it becomes minus Vs. From here if I move minus Vs plus, I assume that the current flowing here is Iz plus Iz into R1 plus Vz. So plus Vz equal to 0. If I want to find the current Iz is equal to Vs minus Vz divided by R1. So this is the expression for current. Now let us analyze what is the importance of this expression. The importance of this expression is, so if you can see here, Vs should be greater than Vs to get proper current. That is, the applied voltage should be always greater than the Zener breakdown voltage. So if you want the output voltage, as 10 volts, so if you want it as 10 volts, of course this Vs value should be greater than 10 volts. So if you give 5 volts and you are expecting 10 volts, that is not possible in this case. You should always give a voltage which is greater than 10 volts here, like 12 volts, 13 volts, 15 volts, 20 volts, like that. you should give a larger voltage to get this Vz. So Vs should be greater than Vz. Next, Iz. So what is the current? What should be the current value? The current value in this circuit should be such that, so you have an expression or you have a relation here which says that it should be greater than the minimum reverse current. It should be greater than the minimum reverse current and it should be less than the maximum Zener current. So if your current value lies in between these two values, then your voltage regulator circuit will work properly. Then the circuit will work properly. So this is what about Zener diode voltage regulator with no load. Now, this is a circuit for Zener diode voltage regulator with load. This is the circuit for Zener diode voltage regulator with load. Now, how does it work? So, coming to the circuit diagram, you have voltage source Vs. Vz is the Zener diode. RL is the load resistance. I1 is the current flowing through R1. Iz is the current flowing through Zener diode. IL is the current flowing through load. Now, at this point, if you apply KCL, that is Kirchhoff's current law, I can clearly state that. So, I1 is equal to IL plus IZ. That is the amount of current flowing towards the node is equal to away from the node. I1 is equal to IL plus IZ. Now, coming to this is Kirchhoff's current law, Kirchhoff's voltage law. Suppose if I apply the Kirchhoff voltage law, what will be the expression? Again, you will be getting minus Vs. So if I go like this, it is minus Vs plus I1 R1 plus Vz equal to 0. Now, I1 is equal to Vs minus Vz divided by R1. So, this is the expression of current. Here, I can say that the load current raises between no load to maximum. That is, IL can vary between no load, that is from zero load to maximum load. So, what happens to that? That is, I can write this expression, that is Kirchhoff's current law expression star as I1 is equal to Iz minimum plus IL maximum. Iz minimum to IL maximum. We should take care that we ensure that Iz minimum is large enough to keep the diode in reverse bias. That is, this value Iz should be large enough to make this diode to work in reverse bias. This should be in reverse bias. So if it is not in reverse bias, you can't work with it. So Iz should be sufficient such that the Zener diode should work in reverse biased condition. It should work in reverse biased condition. Next is, when the load current is 0, suppose IL is equal to 0. If the value of IL equal to 0, the current I1 will becomes Iz minimum, right? So, Iz minimum. So, you must care, like we should take care that the total current do not exceed the maximum Zener diode current. That is, suppose if you remove the load here, if I remove the load here, that is, as we did in the previous case, we had no load there, right? So similarly, if I remove the load here, if I just remove the load here, the current will be Iz. So this won't be minimum now. You will be having maximum current. So this current should not exceed the maximum value. As I wrote here, it should not exceed this maximum value. It should not exceed this maximum value, maximum Zener current. So if it exceeds, the diode get damaged. If it exceeds, the diode get damaged. So you have to design the circuit such that the current should not go beyond minimum value, and again the current should not go again over the maximum value. So that is, totally by these two analysis I can write Iz minimum or Iz maximum is equal to Iz minimum plus IL maximum. So this is one of the key criteria to manage the Zener diode voltage regulator properly. Next is regulation techniques, like how do we manage the output constant? There are two techniques to manage this output constant. One is line regulation, the other one is load regulation. The first one we will understand what is line regulation. So line regulation indicates that, we assume that, see, these are all assumptions we make, like RS and RL both are constant. That is, if I take the circuit, so if you take this circuit, so RL and RS is the internal resistance of this voltage source. So these two are kept constant. This will not vary. Only parameter that varies here is Vs. Vs will vary. So I told you in the previous case here. So it will vary to 25 to 15 like that, right? So same way here Vs will vary. So it may increase its value or it may decrease its value. If that is the case, then we call it as line regulation. If the variation is in the power supply, if the variations are due to the power supply Vs, then we call it as line regulation. We vary the voltage, input voltage, and record the output voltage. Here what we will do, so suppose this is your circuit, I'll take this circuit and I'll start varying this. So I'll vary this, say this 20 is the mean value, and I'll vary up to 15, and afterwards also I'll vary up to 25. That is 5 volts I'll decrease, 5 volts I'll increase, and record the voltage. What is the output voltage variation? So that is called line regulation. Line regulation is change in the output to the change in the input is called line regulation. This ratio is called line regulation. If you calculate the percentage regulation, you will multiply that by 100. Delta V naught is the variation or changes in the output voltage. Delta V in is the changes in the input voltage. So this is line regulation. The key point is we assume that RS and RL are constant. Only varying parameter is power supply. Only varying parameter is power supply. This is how you calculate the line regulation. Regulation using load regulation. So if I am using or if I am calculating regulation with respect to load, I can assume that you can have full load. So you have a load here, or you have no load. Either you have zero load or you have full load. So what is the output voltage when you apply full load? 2. What is the output voltage when you apply no load? Here you don't have any load, you don't have any resistance. Then what is the output voltage? Next, what is the output voltage when you apply full load? So we take these two parameters, no load and full load, and calculate the value of percentage load regulation. This is voltage when you have no load minus voltage when you have full load divided by voltage when you take no load into 100. Here we assume that Vs, that is supply voltage, is constant. The supply voltage is not changing here. It is kept constant. Now this variation or this change will give you the load regulation. So this load regulation and line regulations are the two parameters that decides how good or how stable the circuit is. These two shows us the stability factor, how stable the circuit is to the variations in the load, to the variations in the input voltage. What happens when the input voltage varies? What happens to the load varies? Then these two factors decides and tells us how stable the Zener regulator is. This is all about Zener voltage regulators and Zener diodes. Next topic is voltage regulator. So there are different ready voltage regulator available in the market. That is, in the market you will directly find the voltage regulators for the required voltages. Say for example, LM7800 is one such series where you have different output voltages for this regulator. LM78XX is a general regulator series where XX represent different types or different values of your regulations. Say for example, XX, if you write it as 0, 5, 0, 6, 0, 8, 10, 12, 15, 18 or 24. So if I write LM7824, it means the output voltage is always plus 24 volts. Plus 24 volts. It will not change. The output voltage remains constant. Suppose if you write instead of 24, if you write 08, the output is plus 8 volts. So it remains constant. So this is one such series. Now let us understand how this LM78XX voltage regulator work. This is a simple block diagram of your voltage regulator. That means it is, you don't have all the specific details here, but you have a simple block diagram that shows the functionality. You have a pass transistor here. Pass transistor is a simple transistor. This is a transistor, pass transistor, where you give certain voltage here. Say you are giving V in here. So according to the, depending upon the voltage what you give here, the current or the voltage will be allowed to flow to the output point. So this is simple pass transistor. Pass transistor is a simple transistor that allows the input voltage to flow towards the output voltage depending upon the base voltage what you give. Next is thermal shutdown and current limiter circuit. Thermal shutdown and current limiter circuit, it has an importance here. That is, because you are dealing with little voltage and the current parameters here, whenever the device get heated up, say more than the specified value, suppose for this it is given as 175 degrees centigrade. If the temperature crosses this limit, or if the device get heated up more than this limit, then the current limiter will turn on. Current limiter in the sense it will block the current. It will just make, or it will just break the current, break the circuit, so that the device shut down itself. It will shut down itself. So this is what thermal shutdown and current limiter says. Next is this one. So this is an op-amp. It is an op-amp. So how do you write an op-amp? Like this. It has two terminals. One is plus and minus. That is, it is non-inverting terminal. This is inverting terminal. Non-inverting, inverting terminals. These are for the power supply, and this is the output point. Regarding this op-amp, we will study in the further classes. Now here we will consider as op-amp as a comparator. It is as a comparator. Operational amplifier is working as a comparator. It compares the input, whatever you give to this point and give the output. Comparison, it will make the comparison and give the difference to the output. Now, and this R1 and R2. So look at the circuit. You have V out here and R1. This is R2 and you have grounded. From this point you are giving to the op-amp, right? So R1, so this is R2 and this is R1. Okay. So now look at this. Applied voltage here is V out. V out is the applied voltage. This applied voltage is now dividing into two parts. R2, across R2 it is dividing, and across R1 it is dividing. So it is dividing into two parts. What is the output voltage you are getting here? That is, that will be according to your voltage divider equation. So based on the values of resistance R1 and R2, you will be getting the output here. Okay. So this is a voltage divider circuit. This is an voltage divider circuit. So what is the output voltage here you will get? That is V out into across R1. So R1 dash divided by R2 plus R1 dash. So V out into R1 dash divided by R2 dash plus R1 dash. So this is the equation, or this is the expression for the voltage at this point. Now coming back to the analysis. How does the circuit work? Now coming to the analysis back, here if I see that the output voltage is given to R2 and R1, you will be getting a voltage here, right? Because of the voltage divider circuit, you will be getting a voltage here. So this voltage is compared with the reference voltage. We compare these two with the reference voltage. This will be compared with the reference voltage. That is, and you will get an output here, which is VE. VE is the error voltage. VE is the error voltage. VE is the error voltage, which is equal to, see here, V reference is given to positive. This output is given to negative. Therefore, the error voltage will be equal to V reference, that is plus V reference, minus V out into R1 dash divided by R1 dash plus R2 dash. So this is the error voltage. This is the error voltage. The error voltage should normally be equal to 0. It should be equal to 0. If there is any change in the error voltage, suppose VE is some 1 volt. It means that you have some error here. So reference voltage is greater than the output voltage. Reference voltage is greater than the output voltage. It means that your reference is more, output has been decreased. If VE is minus 1 volt, it means that output voltage has been increased and your reference voltage is decreased. That is, if you want 5 volt output, I will take V reference as 5 volt output. So, the output voltage will be greater than this value. So, it will be greater than this value, then you will get positive error. Sorry, if the output voltage is less than this value, then you will get the positive error. If the output voltage is greater than this value, then you will be getting the negative error. So, like this, you will be getting this error signal. This error signal is given to thermal shutdown and current limiter, and then it will be given to pass transistor. Based on the error signal, the amount of voltage will be passed to the output, and hence your output is rectified. This is how the output will control, or the error signal will control the output. This is about voltage regulator.